right, so athletic field soils and how to manage them. I'm going to talk about a few things in general, and then I'm going to talk about some of the physical and chemical and biological properties that we can manage, give an idea of how to measure them and how to manage them. Let's see that. Okay. So, what's different about athletic field soils? They're different from agricultural soils in that we don't have an opportunity to till them up and open them up every year or every few years if you're using no-till or low-till things. We just, we never, other than aerification, we don't have a way to cultivate them very well. And so we end up with organic matter accumulation in the surface. We end up with compaction from traffic and we can't just go in and relieve it all at one time. And athletic field soils differ from turf soils in that they're exposed to much more traffic. We also have very high expectations for our athletic fields, receiving even though they get a lot of traffic, we're still expected to produce a high quality field. And I thought of one place to start if you needed a little soil information about your site. As you think about athletic soils, most of the fields you're managing probably aren't built with on-site materials or not built from a soil that is in place. Could be on site, probably was maybe built with a process of cut and fill. They probably cut off some of the high points, use that to fill in some of the low points. Maybe they brought in material to build your fields from. So they're probably not just straight up native soils being used in place. But it's still very useful to know about the soils that you are dealing with either as a base or what did the site look like before we had athletic fields on it. And so there's a web application out there called Soil Web, easy to download. You push a button on it, it says get soil data, and this will be what comes back. So I did this for the research plot that I was just showing you. Came back that the soil there is mapped as a Marietta fine sandy loam. It is a fluviquentic Utracrept floodplain soil. Would have normally a horizon sequence with two AP horizons, so it's probably been plowed at a couple different depths or worked at a couple different depths. Below that, we have a B horizon, a few that are fairly well expressed. But also tell you about your soil textures, your soil taxonomy. Gives you an idea. Well, okay, my soil here is a floodplain soil. So I know that at times this is going to flood. Sometimes you might be removed, you've never seen it flood. So this gives you some ideas about what might help me or how did my site evolve. But again, most of us now are working with non-native soils, something that was manipulated. So this gives you an idea of what was there before it was manipulated. So that's Soil Web. But I wanted to just talk about what's the role of soil in plant growth. We need a quality soil is going to be the foundation of which our athletic field is built. Our soil is our reservoir for water. If soil did not hold water, it would be very difficult for our plants to grow. So it's got void space to hold water. It's our supply of nutrients. Most of our nutrients come out of our soil organic matter. A few like P and K, like potassium, calcium and magnesium might be contained in some of our soil minerals, but most of the others are going to come in via the organic matter. It provides anchor and support to our turf grass. The pore space in the soil provides oxygen for our plant roots, which have to breathe. They don't photosynthesize. They need oxygen. And there's been a lot of talk recently about soil health and soil quality. And some people use these terms interchangeably. To me, they are different. The state of health in a soil depends on many other things. An arid soil can be perfectly healthy as it is, but it's not very productive. It wouldn't be seen as a high-quality soil. But it would be very healthy for what it is. A desert soil out in the desert, it's going to have a level of productivity, just not a very high one. So, our soil is going to function biologically in many things in these biological activity. We see a lot of biological diversity. If you want to examine the biological diversity this summer, we were growing in a new NTEP green study. And I went out to pull a bunch of little weeds that were coming up in a few of our plots, and as I sat down on our green plots and started to look around and just watch, the amount of insects that were on that plot was absolutely just amazing. All kinds of little insects, things that looked to me like fleas, red velvet ants, probably about 5 different species of ants were in this little 5 by 10 plot that I was working on. And, that's just the insects. And you have a fungal community associated with this, and bacteria, and maybe some little weed, the little weed plants that I was pulling. So there's just a huge amount of biological activity and diversity going on. They're pretty, good soils produce good production. They regulate and partition water use and solute flow. They alter and buffer and degrade things. They immobilize things that might be toxic. And they cycle through organic materials. They store and cycle our nutrients and other elements. And they provide, and this is kind of getting off into socioeconomic structures. But our soils are supporting that because we are part of the socioeconomic structure. So for soil quality, the simple definition might be the capacity of a soil to function. Its physical, chemical, and biological characteristics. USDA now has a kit for measuring soil quality, and we'll see more measurements of soil quality coming into our work. Soil quality more encompasses the biological properties of a soil than what we are used to measuring. We're used to measuring physical properties. I'm going to talk about physical properties, bulk density, texture, infiltration rate, aggregation, and our chemical properties like pH, electrical conductivity, nutrient levels. But we haven't paid as much attention to biological activity. We're going to see more of these types of measurements. One place we are starting is with soil respiration. And so what we do there is capture the gas coming out of a known area of soil, and then we look at how many pounds of CO2 per acre per day are liberated, are being turned over by measuring the carbon dioxide. If you look very low activities, virtually sterile if we're at 0. If we get less than 9.5, we have a soil that is depleted of organic matter. As we go up to 9.5 to 16, we have somewhat depleted, and we get approaching from or declining from the ideal state, depending on which way we're going. The ideal state is defined as 32 to 64 pounds of carbon per acre per day being respirated. If we're over that, that means we've probably added some kind of organic amendment, and we're breaking that down. So some of my colleagues are starting to do these types of measurements, and we'll see more of this in the future. So in our soils, we've got mineral matter. These are the sand, silt, and clay particles. They're inorganic. The organic fraction, the living and dead plants and animals. We have water, and we have our soil air. And our soil air is very much like the air we breathe, except it is probably higher in carbon dioxide, a little lower in oxygen, and probably at 100% humidity. We may or may not have some of these gases like methane or hydrogen sulfide that we would have if we were in a very poorly drained soil. So I'm going to just talk about some things that I would like to know about my soil that's going to help me manage them. And thing one and thing two are particle size distribution and gradation of those particle sizes. This is going to give us a lot of information, how our soil is going to behave, and give us some insights into cultural practices. This is a test. You can send your soil in and have it run with a soil hydrometer test at a soil testing lab and do some sand sieving. And there are many ways to interpret these results. As agronomists, we're very used to looking at how the USDA approaches things. The engineers have a little different take on soils. So we probably had these done. Our sands material from 0.05 to 2 millimeters. Then we can separate these out into very coarse sand, medium sand, fine sand, and very fine sand. And if you want to remember these, think of a monetary system: $2 to $1, $1 to 50 cents, 50 cents to a quarter, quarter to a dime, dime to a nickel. Knowing the distribution of these particle sizes also will tell us about how our soil, especially if it's a sandy soil, will pack. We'll talk about rounded versus angular particles. And most sands are dominated by quartz, very stable minerals in the soil. The other one we measure is clay, the less than 2 micron fraction. Has plate-like structure, has a high surface area, may even have, some clays have a internal surface area as well as a external surface area. It's what the clays that shrink and swell. These are secondary minerals. They form at the surface of the earth. They form from the breakdown products of rocks as they weather. They have a negative charge, and this gives CEC to our soil and allows us to hold positively charged nutrients. That cation exchange capacity is the sum of exchangeable cations that our soil can absorb. There are 2 sources of CEC. Clays are one, organic matter is the other. Because these clays have a very high surface area, they also have a lot of surface area for water to adhere to, so they help us in holding water. Then between the silt and the clay the sand and the clay, we have silt. Mineralogically, I like to think of silt as just being micro sand. It's usually just very small sand particles that fit between the silt and the clay. And USDA has helped us define, a soil textural triangle, looking at, so you put percent sand along the bottom, percent silt, percent clay. If you know 2, then you know the third, and you can put your percent sand, silt, and clay after you determine them onto this triangle, and then get a textural name. If you're down in this corner of the triangle, you're very sandy, you have lots of options. And you should have a soil that, other than it being grouty, will handle compaction better than most of the rest of that triangle. Also, if we're over in this region, we have options as far as modifying our soil to bring in more sandy material to make it improve its drainage, to make it sandier. If we're in this part of the soil textural triangle or up in clay, up in, you look at that textural triangle and this line that separates the clays from the loams is at 27% clay. The line that separates the clay loams from the clays is at 40%. So you don't have to be 40% clay to be considered clay. So clay has a lot of power, a lot of influence on our soil properties. But as I was trying to get to, if you're over here in these groups of textures, soil modification is going to be very difficult because you just don't have enough sand particles. When we try to modify soils with sand to loosen them up a little bit, we want to get sand particle to sand particle contact, and we just don't have enough sand particles over here, and even if we bring in a lot of sand, we still don't have enough. So if you are dealing with non-sandy soils, probably our best bet for opening them up, for managing their properties, is to add organic matter. The engineers look at soils a little more differently. They consider sands to be anything around a 1/4 inch or 0.072 millimeters, and then they have fines, things below 0.072 millimeters. So they kind of break it somewhere, in the fine sand to silt category, what they look at. So, if you've got a lot of silt and clay, they consider that a fine soil. And they use mostly a dry sieving test, whereas we use the hydrometer wet test. And so they do a sieve analysis. We also do a sieve analysis of our sands and separate it out on that monetary scale that I talked about earlier. But I want to know about, especially if I have a sandy soil, the distribution of particles within the soil. I want to know my sand, silt, and clay, but I also then want to know how my sand is distributed. Do I have a well-graded sand? Well-graded sand, I think this comes out of the concrete industry, but they talk about having a good distribution of particle sizes. What I want is a poorly graded sand. Usually you don't want to be poor. In this case, you probably do. I want a bad distribution of particle sizes. I want a uniformly graded sand with only one particle size or dominated by particle sizes. Gap-graded sands, that's something that the concrete industry loves, but isn't really in play here. So my well-graded sand or my well-graded soil has particle sizes of all different particle sizes. We got big ones, we got small ones, and they all fit together. And the big ones, or the small ones, start to fit in the holes between the big ones. And so we don't get good drainage. We get something that compacts readily. In our getting a non-well graded or a uniformly graded sand or soil, we're dominated by one particle size. There's not a lot of other particles to fill in the holes when that starts to pack together. And because all the particles are about the same size, it doesn't compact really well. And then the gap-graded sand, that makes good concrete. So we want a poorly graded sand. We want something that has a lot of the same particle size, that's uniform. And then we want to look maybe at grain shape if we can. And this is kind of neat to do if you can clean up your soil and look at it under a microscope. And, you see that they're either angular or subangular. Are they really pointy? That's what angular would be. Are they subangular? Are some of the points coming off? Are they rounded? Or are they plated? That's our clay materials. And maybe some micas. If you have some large pieces of mica, I can remember some soils that we dealt with on the Virginia Piedmont when I was a graduate student that had sand-sized pieces of mica in them. Had other exposures of mica throughout the soils in that part of Virginia. But our angular sands, very pointy. Subangular, we're starting to round those points off. Sub-rounded, we've got most of those rubbed off. Very few points, and rounded, very few. So if I've got an angular sand, it's going to pack, and when that starts to pack together, those points start to hit each other, and it kind of sets up, and it gets firm. And we want some firmness in a field. Probably not as firm as we're going to get with an angular sand, but something with a subangular or sub-rounded. If we have rounded particles, they don't pack together very well at all. It's kind of like little ball bearings. So to keep a rounded sand, to have a stable surface on a rounded sand, takes a little work. A lot of times when you see new fields, a new sand field especially, they start to, first couple of years they use them, they have blowouts. As time goes on, we get a little more organic matter, a little more things that stick those sands together, and the rounded sand doesn't become as much of a liability as it was. But in those first early days or times of that field, it takes a while to get that surface stable. So I want to know my soil texture, my percent sand, silt, and clay. And this is going to be influenced by the parent material. That's where soil web might help you. What rocks weathered to make the soil I have. Clay formation, transport of clay into our lower horizons, erosion and sedimentation. Again, we use the soil textural triangle. And, we're working with a soil profile. So usually at the surface, we tend to have maybe a little coarser texture. As we go down, we increase in clay as the clay, or as minerals weather out of the surface layers, clay is deposited in horizons further down. It's common in construction to take away the topsoil and either stockpile it and bring it back, or sometimes they just sew it off and then they start to build in the B horizon. It would be good to know that if that was what happened at your site. Texture determines pore space, aeration, water retention, how much water is available, runoff versus erosion, water infiltration and percolation. Is our soil going to be plastic and cohesive? Will it have shrink-swell character? Or will it not be cohesive and just kind of be easy to work? Here's some pictures. These are old from Washington State University, but here we're applying water to each of these soils. The water application time is the same. We can see that the sandy soil has much less surface area, so as it coats with water, water moves faster in that, or the wetting front moves down faster in the sandy soil. The loam has a little more fine material in it, doesn't move quite as far, and then our clay soil, water movement somewhat restricted. It has a lot of surface to wet up. Here we applied the same amount of water. So maybe this is even a better measurement of surface area. The sandy soil has the smallest surface area to wet up. The loam is intermediate, and then the clay soil. Soil texture will help us with determine soil structure. Our sandy soils tend to not have good soil structure. Our more clayey soils, silty soils tend to have a little better soil structure, tend to form aggregates that give us secondary soil structure to help us with soil water movement and air movement. Soil texture will tell us a lot about tillage, how we're going to respond to that. Our microbial activity and organic matter compound. Somewhat our pH. Sandier soils tend to have lower pH. It'll influence soil temperature and soil productivity. So how can we manage soil structure? We can improve soil structure through time with a top dressing and holotine aerification approach. But it takes time, it takes diligence. If we don't have a soil we like. Otherwise, sometimes maybe we don't have the resources or the opportunity to add sand regularly. We kind of have to manage what we have, but the information of knowing your soil texture is going to be helpful. And, if we have the opportunity, we can manage this up front by choosing a good soil to start with and building our root zones from quality materials. So if we're in a construction situation, we have an option to improve. The next thing I want to know is, what is my bulk density and is my soil compacted? The most common way to measure this is with a core sample. We pull the core of a known volume, we take it back to the lab, we dry it out. Now we have a mass of soil and a volume of soil, and that's what bulk density is. The amount of soil in a given volume. So, this characterizes soil structure, tells us about our pore space. The more pore space, the less dense our soil is, the lower the bulk density. Texture will influence this. We'll see a slide of that in just a minute. Range for mineral soils, about 1.1 grams per cubic centimeter to 1.5. This is where I'd like to have my athletic field soil, and that's 69 to 94 pounds per cubic foot. Now, density is influenced, and this is from engineering. Every soil has a curve in which they start with a dry soil, they start to hydrate it, and then they expose it to compaction. And as it becomes more hydrated, they keep adding the same amount of compaction. And as it becomes more hydrated, it gets denser and denser. Our unit dry weight goes up until we hit a maximum unit dry weight. And that point is usually somewhere around field capacity for a soil. Field capacity is our water content about 2 days after a rain in a moderately textured soil is about a day after a rain in a sandy soil. So we like to keep our soils around that, that's a nice wetness, but it's also kind of getting to be the most compactable place for the soil. After we get to that maximum dry weight, it says on that diagram, swell. Now we've got extra water in the mix. Our pores at that point are filled, and so our soil begins to swell, and we can't compact water. And when we try to compact water, the grains in the soil start to fall apart, so our density goes back down until we get over to saturation. So here's one of those curves for a soil, and if you remember the data from the last slide, it was saying an ideal density there is about 94 pounds per cubic foot. Here we're up to 116. So this is getting very compacted, and it's somewhere around 15% moisture. On the side of this is a line that gives us zero voids. That's our sand weight, 270 grams per cubic centimeter, our zero void rate. So here's a number of different soils, and they're kind of compaction curves. We know this one up at the top. Says well-graded clay sands and gravels. That's our baseball infield. Usually we're using a well-graded clayey sand for infield material. And you can see that there, you can really get that thing to compact. Densities of up over 2.2 grams per cubic centimeter, about 140 pounds per cubic foot. That's why we use them there, because they're pretty stable. They respond good to compaction. The other one we use is down here, number 5, uniform fine sands. And this illustrates the point that if we have a fairly uniform fine sand, it does not compact well. We see over a range of compaction levels that the density of this really does not change very much. And that's why their uniform fine sands are used in athletic field construction. So here we're looking at our different soil textures, and this gives a ideal bulk density, and then the bulk density at which root growth is affected, and then at which it stops. We can see that our sands and loamy sands, we can get away with a little more compaction, a little firmer surface, a higher bulk density. As we add more clay, as we go down this chart, we have less and less wiggle room. Our ideal bulk densities become lower. If we're dealing with clays, this is a pretty less than 110. That's pretty loose. Bulk densities of 1 point. This is about 50% pore space, 50% solid space. So we've got less wiggle room here in these finer soils than we do in our sandier soils. How do we best manage this? Hollow tine aerification. I think of hollow tine aerification, to steal from Dr. Rogers at Michigan State. This is one of the few things that we do. Everything we do to turf is on the horizontal plane. This is one of the few things we do in the vertical plane. I think of this as we're doing all these things on the horizontal plane. We're pushing down that soil. Not a lot. I'm talking about maybe a 1/4 inch or maybe less than a 1/4 inch. We're getting compaction. And that compaction goes down in the soil a little ways, maybe to 6 inches. But we're compacting. So if we could take a very good laser transit out there, maybe we could measure that we have lowered our surface a couple millimeters. When we aerify, when we pull these cores, we open up pore space, we bring these cores to the surface, then we process these cores, top dress them back, put them back onto the surface. I'd like to think that we have raised now our surface. So we pushed it down 3 millimeters. Now we pulled these cores up, processed them. We added those 3 millimeters back. We put in some holes we created these large soil pores. So now we are back. We've removed the compaction and we're back to level. And that's why this is such a vital, this should be the cornerstone of your density, your compaction management. Whoops. So all the good things it does, it punches a hole, reduces compaction, loosens things up. It has the potential to break down thatch, creates a large pore, breaks through layers if we have them, and adds material. We're adding material to the profile. Next thing is a chemical property, pH. Scientifically, it's the negative log of the hydrogen ion concentration. We're measuring the acidity or alkalinity. Our pH scale, 7 is neutral. Below 7, we're acidic. Above 7, we're alkaline. Here is a diagram of some common things that we might be familiar with. Battery acid way up at the top actually has a negative pH. It's a very strong acid, H2SO4. So you can have a pH that's negative. It's very, very rare that we see acids that strong, but It does happen. So you got gastric fluid around pH 1, vinegar about pH 3, pure rain in equilibrium with carbon dioxide, pH of about 5.3. Freshly distilled water. So freshly distilled water hasn't had time to interact with CO2, so it has a pH, it's neutral, pH 7. Seawater about pH 8, baking soda a little above 8. Limestone or pH of limestone soils should be about 8.3. That's calcium carbonate in equilibrium with water. Household ammonia, high pH, all these things. These things down here will burn you pretty bad. So that's on the high end. We don't see a lot of that. We usually see things 8.3 or lower. Anybody dealing with a pH above 8.3? We get up above 8.3, now you're thinking of sodic soils where we're having to deal with some sodium. And that's probably a whole nother talk. pH gives us an indication of weathering. Lower pHs we associate with things being more weathered. Give us the availability of nutrients. Toxicity of metals, especially aluminum, and how oxidized or reduced our sulfur might be. So you've probably seen this diagram before of the availability of different elements or different nutrients varying with pH. Extremely acid on this end, extremely alkaline on that end. When we start to look at, we want to keep things around pH 6.5 or so because that's when all of our nutrients are most available. It's also when our microbes work the best. A lot of times when we see a soil that is building up organic matter, we look at the pH and it's usually on the low side. That means our organisms aren't working as well as they could be. Usually if we raise the pH of that soil, the organic matter accumulation may start to break down a little faster. We measure when we take the pH of a soil, and pH meters are getting cheap. You can buy a little stick pH meter now for $100 if you want to know your pH. pH test in a lab should be part of a normal soil test, but we're measuring the H plus in solution. We also would like to know about exchangeable acidity and maybe reserve acidity, but especially the exchangeable acidity. And that's what we measure when we measure liming requirement. So pH tells us where we are. Think of it as being the tube on a big coffee urn. So the pH tells us where we are, how full is that urn. But we don't know anything about the size. Our exchangeable acidity, our buffering capacity, that's how big that coffee urn is. So if you had a coffee urn that only held 2 cups and it was half full, there'd be a cup of coffee in it. If you've got a coffee urn that holds 20 gallons and it's half full, you got 10 gallons of coffee. So, if we drink a little coffee, it's the first one, we can start to really lower the pH. If we drink a cup of coffee out of the second one, it doesn't make much of a dent. So we need to know our buffering capacity as well as our pH. Now, the driving force of soil pH is aluminum and its state of hydrolysis. So at lower pHs like pH 4, aluminum exists as aluminum plus 3. It splits water and kicks out H plus acidity. As we raise our pH to about 4.5 or so, now our aluminum exists as ALOH, 2 plus. That splits water, spits out more acidity. And then here about 5.5, we get another hydrolysis reaction. So for every aluminum ion we get, it has the potential to generate 3 moles of acidity at different pHs. As we raise our pH to above 5.5, when we get to 5.5, our aluminum gets into ALOH3. This is a mineral called gibbsite. It precipitates out, and it doesn't affect our pH. So to avoid aluminum in solution, we manage soils at above pH 5.5. And, Al plus 3 itself, when we get into those low pH regions, aluminum is toxic to roots. So other things that acidify soil, CO2, we kind of saw that from respiration. H plus from cation exchange. Our plants will kick out a hydrogen ion if they want to take out like a potassium ion or calcium. You have to have an equal exchange, so we release acidity from our roots. As we leach away ions like calcium or chloride and sulfate, they require a leaving ion to keep things positively charged, so we lose basic cations. They're replaced by H+. Oxidation of substances, especially sulfides, reduce things. Acid rain. And our buffering capacity, that liming requirement, that's our resistance to change. And the exchange sites are in equilibrium with the soil solution. So the higher CEC, the greater our buffering capacity. To manage pH, usually we're increasing alkalinity. We're adding lime, we're adding OHs to the soil, we're recycling bases. So liming is how we are going to manage our pH. When we raise the pH with lime, we're adding things that have calcium carbonate, maybe magnesium carbonate in them. What does the neutralization of the acidity is the CO2 part. We're making carbonic acid that then dissolves into carbon dioxide and water. If you're in a pinch, these other lime materials can be used, but I would stick with agricultural lime if I could. And here's what's happening. So we've got our soil colloid, it's got acidity on it. We add lime, we're adding a bunch of calcium carbonate. The calcium knocks the acidity off our cation exchange sites. Now our cation exchange is dominated by calcium. It knocked the aluminum off the chain sites, precipitates out as gibbsite, and then all that H plus that was there reacts with the carbonate and goes off or becomes water and carbon dioxide gas. It's the carbonate part of lime that is the active agent. Calcium does not neutralize acidity. You cannot, things like gypsum are not liming materials. They don't change soil pH. Calcium carbonate does. We have to generate hydroxyls that neutralize acidity. So, sandier soils, less buffering capacity, less clays, less CEC. Clayier soils, more buffering capacity. So to change from pH 5.5 to 6.5 in a sandy soil, 55 pounds of lime per 1,000 square feet would take you 100 pounds on a clayier soil. What determines how much lime we're going to turn on, how much pH change do we need, how buffered our soil is, how good the lime is. That depends on the purity of the lime and also the fineness of the lime. Finer grinds will change your pH faster, but they're harder to handle. They're dusty. I like nice pelletized lime. It doesn't have a lot of dust with it. It's easy to spread, but that takes 3 months to change the pH, where very fine, dusty lime might work in a month. If we're going to lower pH, we can do some of these things. We can add organic matter. We can add ferrous sulfate or use ammonium fertilizers like ammonium sulfate. Or we can use elemental sulfur. I'm running a little behind on time, so I'm not going to get into too much of that. If you got to do that, it's very hard to keep your turf surface and add elemental sulfur and bring the pH down. Can be done. Next thing I want to know, surface hardness. To me, surface hardness differs from compaction. Compaction deals with turf growth. Hardness is a safety issue. Kind of the same thing, but the surface hardness is right up at the surface. We usually measure this with this Clegg impact device. Get a number here. This one, what did I get, 5.5, not compacted. If we get a number on this device above 10, we multiply that number when we report it by 10. So if we start to report hardness is higher than 100, we're starting to have problems. What's that? About 10 minutes? Okay. So to manage hardness, we can water. If it's too dry, we can aerify quickly with small tines, grow more grass. That'll reduce our hardness. Top dressing. I'm going to go through these next ones quickly to be able to answer some questions. So organic matter, to manage this, it's an accumulation of organic matter at the surface, of humus and things. Normally organic matter is good, but sometimes if we accumulate too much, it can be something we've got to deal with. The C to N ratio is very important to tell us whether organic matter is going to break down or is it going to stick around for a while. We would like to have C to N ratios of around 10 to 20. If our C to N ratio is less than 20 to 1, we'll get N release. If we get up above 30 to 1, we'll start to sequester N for a period. And organic matter won't break down. What we're driving toward, what we'd like to get is humus, very stable organic matter. If you look there, it's got a C to N ratio of 10 to 1 to 12 to 1. This does great things for us. It lowers our bulk density. It adds to our CEC. It adds to our water holding capacity. And it's a source of NP and sulfur and micronutrients. Most soils, 0.5 to 7% in the A horizon. So I'd like to know about my water infiltration rate, how fast water gets into the soil. I can measure this. The gold soil texture gives us an idea. If I see I've got a sandy soil, I expect to be over 1 inch an hour. If I see I've got a clay soil, I expect to be less, maybe way less than 1 inch an hour. The gold standard is double ring infiltrometer, but that can be squirrely. And I thought about this the other night as I was looking at this. Pound a coffee can in with the ends removed and measure, fill it with water and measure how fast the water goes down. Works pretty good in most soils except sandy soils. Who's seen a coffee can lately? They're all plastic now. So if you're at a facility with a kitchen, get a number 10 can that the peaches come in or whatever. They're still around, but there ain't coffee cans anymore. Look at your field drainage. Nutrient levels, do a soil test. Stick with the same lab and procedure. Use a lab without skin in the game. So somebody that's independent. There are a lot of nice vendors that will do your soil tests for you, but I'd like to use somebody that would be independent. Keep track of your numbers. See where you're going. Watch the data. Here are just some. If you're reading a lot of recent turf literature, there's this minimal level of sufficient nutrients. That works pretty good on sandy golf greens. I don't think it's for athletic fields yet. So we should be still over here using some of these values from the SLAN method. Number 8, I want to know my grade. I want to know how is my field graded correctly. And sometimes over time we can see these things change. Sometimes we don't detect them and we might have a problem. So I want to know, do I have sufficient grade? I want to look at my soil profile. Do I have a layered profile? Here I've got fine layered over coarse. Notice that water doesn't break through until all of my upper fine soil is saturated. Here I've got a band of very fine soil within some medium texture. This is a restrictive layer. It's regulating the water flow across that boundary. So look for layering. Our solution here, deep tine aerification or other aerification that goes deep. If you're doing things correctly, when you use these things, our drainage will improve. I want to know my thatch thickness. I'd like to have about a 1/2 inch of thatch. If I've got more than that, I'm going to, have to really manage it. If I've got less than that, I'd like to maybe build a little up to give me some cushion. I'd like to know my CEC, and I can get that through my soil test. Usually they'll give you a sum of cations, but really a double wash method would be better, especially for sandy soils. To manage this, add organic matter, compost, increase CEC. If you're in the Mississippi area, our field day this year is going to be September 17th. It's an excellent field day. The Deep South Turf Expo encompasses the states of Alabama, Florida, Mississippi, and Louisiana. It will be in Biloxi, Mississippi, November 2 to 5.